This is the second in a series of videos in which I'll be looking at solutions to questions from CSEC Physics from 2024. Exam was today, right? So this is question 2. Now, question 2 deals with stability, states of equilibrium, and moments. Now, question 2, the first part shows three water bottles, and they're in different orientations. Orientation A, the bottle is upside down. Orientation B, the bottle is right side up. And orientation C, the bottle is on its side. And we're asked to state the type of equilibrium for each of the following. Now, let's examine position A. Now, in position A, if you were to just give the bottle a slight displacement, it will topple over quite easily. And therefore, we say that this bottle is in a state of unstable equilibrium. So in position A, the bottle is in a state of unstable equilibrium. All right. Now, position B is, of course, is the regular orientation. Now, because in position B, the base is broader, and it basically means that if given the same slight displacement as in orientation A, it is not likely to topple over as easily. It may be displaced slightly, but it may rock back into position and basically retain its original position. And therefore, we say that because it does not topple over easily, it is in a state of stable equilibrium, right? So in position B, the bottle is in a state of stable equilibrium. Now, in position C, no matter how you turn or spin the bottle or turn it around, the position of the center of gravity does not change. It does not appear to be any more stable or any less stable than it initially was. And so therefore we say that it is in a state of neutral equilibrium, right? So this bottle in equilibrium. So I forgot my spelling there for a little while. So in position C, it is in a state of neutral equilibrium, right? Good. So position A, unstable equilibrium, it will topple over easily because the center of gravity is relatively high, the base is narrow, and so a slight displacement will cause it to fall or topple over easily. Position B is in the proper orientation, the base is broader, and of course, because the base is broader, the same slight displacement will not cause it to topple over quite easily. It may rock back into its position. It's in a state of stable equilibrium. In position C, however, it is in a state of neutral equilibrium because regardless of how you turn the bottle, the center of gravity will be in the same position. All right. Now, part B of the question says, define the moment of a force. So part B. Now, how do we define the moment of a force? The moment of a force is defined as let me start right. So the moment of a force, the moment of a force about a point is the product of the force and the perpendicular distance from the line of action of the force to the point, right? So that is a comprehensive definition for the moment of a force. So the moment of a force about a point is the product of the force and the perpendicular distance from the line of action of the force to the point. So if you had written this in the exam, you're guaranteed to get your full marks. So this question may have been worth 2 or 3 marks. If you had written this definition, then you're guaranteed to have gotten your 3 marks, right? So let's move on to part C of the question. Now, part C says figure 6 shows a uniform meter rule balanced horizontally. So of course we're told it is balanced, and from that we should know that the forces are in equilibrium. It is balanced horizontally, right? On a fulcrum with a mass of 0.24 kilograms hanging from one end. And we're given that G equals 10 newtons per kilogram. Now, another key word in this question is uniform. The meter rule, of course, is 1 meter long, 100 centimeters. And because it is uniform, it means that the center of gravity is located at its geometric center. If we're talking about a meter rule, then the center of gravity is at its geometric center, which of course would be 50 centimeter from either end. So this of course would be the weight given by mg. All right. We're given that the mass of course is 0.24 kilograms, and we can find the weight, right? But actually the question asks us to do that. So part 1 of part C says calculate the weight of the 0.24 kilogram mass. So this is part C and this is part 1. So now we're going to use our formula. W is equal to mg. So weight is equal to mass times gravitational field strength. The mass is equal to 0.24 kilograms. So W is equal to 0.24 kgs times 10 newtons per kilogram, and therefore the weight is equal to 2.4 newtons. So therefore the weight of the 0.24 kilogram mass is 2.4 newtons, right? Now, do we know the weight of the meter rule? Currently we don't, because in part 2 we're told to calculate the weight of the meter rule by taking moments, right? So by taking moments, we want to calculate the weight of the meter rule. Now, let's look at the diagram here. Now, once again, we know that the meter rule is balanced horizontally, which means that the forces acting on the meter rule are in equilibrium. And because these forces are in equilibrium, we can actually apply the principle of moments. Now, what exactly does the principle of moment state? The principle of moment states that when a body is in equilibrium, the sum of the clockwise moments about any point on the body is equal to the sum of the anti-clockwise moments about the same point, right? And so regardless of which point we take moment about, the principle of moments still applies. However, in this case, it is obvious or logical to take moment about the fulcrum, about the pivot that we will actually label P. Now, let's identify which force is producing what type of moment. Now, the pivot is at P, and what this means is that the 0.24 kilogram mass is going to be attempting to rotate the beam in this direction. And this therefore produces an anti-clockwise moment, right? So therefore the 0.24 kilogram mass, which of course has a corresponding weight of 2.4 newtons, will attempt to rotate the beam in an anti-clockwise direction and therefore produce an anti-clockwise moment about the pivot. The weight of the meter rule, on the other hand, will attempt to push it this direction and therefore produce a clockwise moment about the pivot. All right? So we've identified the moment being produced by each force, and we can now apply the principle of moments to find the weight of the meter rule. So of course we know that the weight of the 0.24 kilogram mass is 2.4 newtons, and we'll be needing that value, right? So we say that taking moments about the pivot P, we say that the sum of the clockwise moments, so the sum of the clockwise moments about P is equal to the sum of the anti-clockwise moments about P. And we'd have already established that the 0.24 kilogram mass, which of course has a corresponding weight of 2.4 newtons, is producing an anti-clockwise moment, whereas the weight of the meter rule is producing a clockwise moment. Now, what is the distance that the weight of the meter rule is acting from the pivot? Now, we know that the meter rule is uniform, and because a meter rule is uniform, it means that its center, or its center of gravity rather, it's at the geometric center, which therefore means that the weight is acting at a point of exactly 50 centimeters or 0.50 meters from either end. And if this distance from the opposite end to the pivot is 0.18 meters, then it means that the distance from P to where the weight is acting at the center of gravity is equal to 0.5 minus 0.18, which of course is 0.32 meters, right? So therefore, it means that the center of gravity is 0.32 meters to the right of the pivot, and therefore the distance from the line of action of the meter rule's weight to the pivot is 0.32 meters, all right? So let's now go ahead and substitute these values into our equation. So for the clockwise movement, we have the weight W times 0.32 meters is equal to 2.4 newtons times 0.18 meters. So 0.18. So we say that 0.32 W is equal to, now 2.4 times 0.18, what does that give us? 2.4 times 0.18, that gives us 0.432, 0.432, yes, 0.432 Newton meters. And therefore we can divide both sides by 0.32. And so therefore we say that W is equal to 0.432 Newton meters. Working this, I just remember that a previous part of the question asked us to write down the unit of the moment, but we can go back and do that. So W is equal to 0.432 Newton meters divided by 0.32. This would be meters, and therefore W is equal to approximately 1.35 newtons. So therefore W is equal to 1.35 newtons. So as I mentioned before, in the previous part of the question, we were asked to define the moment of a force. We were also told to state the SI unit, which of course, the SI unit of the moment of a force is the Newton meter, right? So hopefully, if you forgot to state the unit and you actually use it in your calculation, then the marker would probably give you a blank and say, all right, at least, the person know the unit, get them a blank, right? But of course, the onus would have been on you to remember to state the unit, all right? So is there any more to the question? All right, so we have one last little part of the question. It says, calculate the magnitude of the force of the fulcrum acting on the meter rule, all right? So what have we done so far? We've applied the principle of moments and we've found the weight of the meter rule. Now, the meter rule is in equilibrium. And of course, you know that whenever a body is in equilibrium, there are usually two conditions which must be satisfied. The first one, these are the principle of moments, where we say that the sum of the clockwise moments about any point on the body must be equal to the sum of the anti-clockwise moments about the same point. Now, the other condition is that the resultant force acting on the body must be equal to zero, right? Now, the resultant force must be equal to zero, and in a vertical direction, or if the forces are vertical, we can actually say that the sum of the upward forces must be equal to the sum of the downward forces. So here at this pivot P, there is going to be an upward reaction force. Let's call that R. So there is going to be an upward reaction force. We know that we have the weight of the meter rule and the weight of the 0.24 kilogram mass acting vertically downwards. So this W of the meter rule is equal to 1.35 newtons. The weight of the 0.24 kilogram mass is 2.4 newtons. And therefore, that will allow us to find the value of the reaction force at P, right? So once again, the second condition for equilibrium is that the resultant of the forces acting on the body must be equal to zero. And in this particular case, we're dealing with vertical forces. And we therefore say that the sum of the upward forces is equal to the sum of the downward forces. So the sum of the upward forces is equal to the sum of the downward forces. And the only upward force is the reaction R, and the two downward forces are the weight of the mass, which is 2.4 newtons, and the weight of the meter rule, which is 1.35 newtons. When we add these two, we get 3.75 newtons. So therefore, in order to keep this meter rule balanced, the reaction at the pivot, or the pivot, must be exerting a reaction force of 2.75 newtons, which acts vertically upwards to balance the weight of the meter rule and the weight of the 0.24 kilogram mass. Right, so this is the end of the question. And to be honest, this wasn't one of the most challenging questions on principles of moments and equilibrium. I've seen questions to be far more challenging. So, I mean, a well-prepared student should have breezed through this question. All right? Yeah, it definitely wasn't very challenging for the most part. And we have seen many more challenging questions from the same topic over the years. So hopefully, many students were able to maximize on um, the difficulty level of this particular question.